Hello, friends, and welcome back to my YouTube channel, Electrical Hub. Here, we are going to discuss about the efficiency of electrical motors. The topics that are going to be covered are basics of motor, types of motor, characteristic of motor, type of motor losses, and finally calculation of motor efficiency. At the end, I will show you how to calculate the efficiency of the motor. Basics of motor. Motor, as we know in the industry, it converts electrical energy into the mechanical energy. But how it converts? It converts by the interaction between the magnetic field in the stator and rotor winding. Here we are going to discuss about the different types of the motor that are used in the industry. We will also discuss about some of the motors which are energy efficient. Let us first start with the induction motors. Induction motor is the most commonly used motor in the industry. When a three-phase supply is fed to the stator winding, a magnetic flux of constant magnitude is set up. The rotating magnetic flux, as it sweeps, cut the rotor conductor. Thus, it causes an EMF to be induced on the rotor conductor. Induction motor basically follows two types of laws. One is the Faraday's laws and the other is the Lenge's law. According to the Faraday's law, it is the relative motion between the stationary rotor conductor and the rotating magnetic flux which produces an EMF. And second is the Lenge's law. Since the rotor conductors are shorted and form a closed circuit, the induced EMF produces a rotor current whose direction is given by the Lenge's law, according to which it opposes the direction of the cause. Here, the cause is the relative motion between the rotating magnetic flux and the rotor conductors. To reduce the relative motion, rotor starts rotating in the same direction, but it never catches up with the speed of the rotating flux. Thus, induction motor always runs slower than the rotating flux. It is known as the slip. I request you to kindly like and subscribe my channel. Here you will get a lot of information about efficiency of the equipment and energy management. Now let us discuss about the slip ring motor. Here the stator is same as the induction motor, but the rotor is wounded with the wire coils. The end of the windings are connected to the slip ring so that the resistors or other circuitry can be added to it. The resistance or other circuitry are added to it to increase the initial torque, so it has a very high torque even at zero speed. As the speed increases, the resistance are decreased. The synchronous motor structure is similar as the induction motor, but there are a few differences. First, synchronous motors runs at a synchronous speed, and secondly, the slip of the induction motor is encountered in the synchronous motor by DC excitation. Permanent magnet synchronous motor. It is a energy efficient motor. It is an alternative for induction motor because of better power density, better cooling, smaller in size, and higher efficiency. In the permanent magnet synchronous motor, the rotor is similar to the brushless DC motor, while its stator is similar to induction motor. Here, the windings are arranged such that they produce a sinusoidal flux density in the air gap of the motor, so they perform best at sinusoidal waveform. Synchronous reluctant motor. In this motor, the stator is similar to induction motor and permanent magnet synchronous motor. But here the rotor is built with a simple magnetic material to take the advantage of the reluctance principle. In this case, there is no magnets or current conducting parts in the rotor, so the rotor losses are very less compared to the induction motor. It can achieve IE for efficiency class. Characteristic of motor. Speed of the motor is determined by the formula Ns is equal to 120 by F into P, where F is equal to frequency and P is equal to number of poles. But in the induction motor, it is limited by slip percentage. So the percentage of slip is equal to Ns minus Nr by Ns into 100, where Nr is the actual speed or rated full load speed of the motor. Now we will discuss how the loading of the motor affects on the power factor of the motor. As the load of the motor reduces, active current of the motor reduces, but the reactive current which is required to maintain the magnetizing current of the motor doesn't get reduced. So the power factor get reduced. Now let us discuss about the efficiency of the motor. The motor efficiency is determined by the two factors. One, electrical energy input to the mechanical output, and secondly is the power factor. We will also calculate by an example the efficiency of the motor. So while we are going to calculate the efficiency of the motor, we should also consider the losses of the motor. So the losses of the motor are known as the intrinsic losses. Intrinsic losses are of two types. One is fixed and the other is variable time. Fixed loss. Fixed loss consists of magnetic core loss and the friction and windage loss. Magnetic core loss is due to the hysteresis and eddy current loss, while the friction and windage loss is due to the friction of the bearing and aerodynamic parts. Variable losses are caused due to the resistance in the stator and the rotor winding. And finally, the stray loss. The stray loss, according to the IEC standard, it is 0.5%, and according to the IEEE standard, it is from 0.9 to 1.8%. Stray loss is very difficult to calculate according to the IEEE standard it is considered. And in India, we mostly consider according to the IEC standard 0.5%. Efficiency of motor is determined by the formula power output by power input, or 1 minus power loss by power input. Okay. Now let us discuss about some of the field tests for determining efficiency of the motors. No load test. No load test of the motor is considered to determine friction and windage and the core loss. What is friction and windage loss? Friction and windage loss is the no load power minus I square R. Stator and rotor I square R loss. Stator winding resistance is measured directly by multimeter, but the rotor resistance can be measured by the locked rotor test. But rotor I square R loss are measured by the measurement of rotor slip. So rotor I square R loss is equal to slip into stator input minus stator I square R loss minus core loss. Stray losses, as I said, according to the IEC standard, it is 0.5%, but according to the IEEE standard, it is 0.9 to 1.8%. It is considered as such because it is very difficult to measure. So, according to the IEEE standard, 0.2 1.8 is staged as for 1 to 125 HP motors is 1.8%, 125 to 499 HP it is 1.5%, 500 HP to 2499 HP it is 1.2%, and 2500 HP and above is 0.9%. Now, let us calculate the efficiency of a motor. For example, let us consider the motor specification as 50 kilowatt motor the voltage of 415, current of 86 ampere, speed 1475, insulation plus F, connection delta, no load current is 22 ampere, and stator winding resistance at the rate 30 degree is equal to 0.25. The important thing to note that why we are taking the stator resistance at 30 degree, because the resistance of the winding increases with the temperature. As we know, the resistance RT is equal to R0 into 1 plus alpha T. Now, I will show you 5 simple steps how you can calculate the efficiency of the motor. First, step number 1, calculate the iron plus friction and windage loss. That is nothing but the no load power minus copper loss at no load. At no load means temperature is 30 degree. So the resistance is 0.25. And as we know, the no load power is 1500. So with this formula, we can get that the friction and the windage loss is 1379 watt. Now, step number 2. We will calculate stator loss at the rate 120 degree. Why 120 degree? Because when the motor is running, we are considering the temperature of the motor as 120 degree. It may be less or it may be more, but for example, we are taking it as 120 degree. So now the resistance will be 0.25 multiplied by 120 plus 235 by 30 plus 235, which is equal to 0.335. Thus, stated copper loss at full load is equal to I square R. Means now the current is 86. So the loss will be 2625.58 watt. Now it is very important to know the rotor input power. So how will you calculate the rotor input power? So first we will have to calculate the slip. Slip is nothing but synchronous speed minus actual speed by synchronous speed. Thus, rotor input power will be 50,000. 50,000 is because the motor rating is 50 kilowatt by 1 minus S slip, which is equal to 50813 watt. Now, step number 4, the stray losses. Stray losses we are considering 0.5% as per IEC standard. So the losses is equal to 0.005 multiplied by 50 kilowatt is equal to 250 watt. Now we will calculate the motor full load input power. It is the rotor input power which we have calculated by output power by 1 minus s plus copper loss at 120 degree plus friction and windage loss plus stray losses. So it means that the motor full load input power is equal to the rotor input power plus all the losses. So it will become like 55067.581. So now it's become very easy to calculate the efficiency of the motor, which is power output by power input is equal to 90.79%. And similarly, with the same data, you can calculate the power factor of the motor, that is power input, by 1.732 into 450 into 86, that is root 3 VI is equal to 0.89. Thank you, and I request you to please like, share, and subscribe. If you have liked the video, please share and subscribe. Thank you.